In the previous video, we talked about the mechanical analog for nuclear magnetic resonance experiments, and we saw that it was made out of a simple harmonic oscillator, and it generated the same signal as the description of the NMR experiments in the classical and quantum approach. Today I'm going to show you a little bit more about the analog and some experiments we can emulate using it. But before we start, let me show you the mechanical analog. So here in the camera, we have the mechanical analog. So here is the spring, the structure. This is the two magnets connected by the aluminum rod. And we have here the two coils, the detection and exciting coil and the damping coil. Here we have a circuit and the Arduino Mega. And here we have a potentiometer attached to the servo, so we can change the damping factor of this damping coil. It is connected to the computer, so we can see all the plots in Excel program and control it using a PLX-DEC macro in the Excel, which is the interface we are going to use to control the experiment. Let me show you in the computer. So this is the Excel program I was talking about. With the macro installed, the PLX-DEC in the Excel, you have to click Ctrl+Q. If you click Ctrl+Q, you will open this interface here, which you will use to control the experiment. So you have to know the Arduino is on and the baud rate of our program. If you click Connect, then you have to send some data, like the number of points you want to get, and some other information about the experiments, and you just need to click Send Parameters. And then you can start to do the experiment. So you can see here we have three buttons and the reset row button. And if you click in one of these with the parameters, you will do a certain experiment. So let's start to see what experiments we can do with this mechanical analog. The first experiment I'm going to show you is the dead time experiment and the first signal detection that emulates the signal of an NMR experiment. So we talked about the signal in the NMR, and we said we need a pulse to make it start oscillating. Here, we also need a pulse to make it start oscillating. But if we give a pulse and start to measure right after the pulse, what we're going to see is the transient of this pulse, and it will be much greater than the signal. And this makes it harder to do Fourier transforms of our signal, because then it will start to appear frequencies that doesn't relate to the sample itself. It's just because of this transient period here that we didn't wait it for. So this is called the dead time, and we have to wait for this before collecting the data. Otherwise, we're going to see a bandwidth. So if we don't wait for the dead time, what we're going to see in NMR experiments and here in our analog is that we are going to have frequency that doesn't relate to the sample. They are not. So let's see this in practice in our program. So to do this, we're going to use the dead time button here. And let me change the camera for the analog so you can see it oscillating. I'm going to click in the dead time experiment and we can do it right now. So as you can see, it starts to measure right after the pulse, and then we have the signal coming from the oscillation. You might say that the oscillation is very small and you don't see in the experiment. This happens because we cannot let the capacitor discharge for a great amount of time. Otherwise, we are going to break the digital analog converter of our Arduino. So we have to give just a little pulse of the capacitor discharging. Otherwise, we are going to break. So the oscillation is very small, but our system is very sensitive. And I can show you that it is actually measuring by doing it again. So I'm going to reset row. So you see we reset the rows. And then I'm going to click in the dead time experiment. Let me do, and it starts to oscillate. So you see it is actually measuring the oscillation. I'm not cheating. It's just that the oscillation is very small for our eyes to see in this case, but it appears. So this is the first experiment you can teach using the mechanical analog. Let's go to the next experiment. For the next experiment, we are going to use a 100 ohm resistor in our NMR analog. So we talked about the dead time, and now we know why we have to avoid the dead time transient. And now we can say to our students, well, let's talk a little bit about the magnetic resonance signal. So without a dead time, we're going to see an oscillatory motion with a decay. But we have two ways of seeing this oscillatory motion with a decay. In our own resonance detection signal mode and in our off resonance detection mode. In our own resonance detection, we don't see the oscillation, we only see the decay. And it's important when we only want to look at the relaxation times, for example. When we want to see the oscillation, we have to do an off resonance detection. So how are we going to show this in our analog? We're going to show it by making a signal. So let's do it. Let's go to the camera and to the program. So here we are in the program, and I'm going to put a 100 ohm resistor in the damping coil. So now we are going to have a damping in our system, and we're going to plot a signal. So let's pick the signal. I'm going to click here in the fixed value resistor button, and now we can see it starts to oscillate. Here we see the oscillation, and it's being damped by the damping coil due to the shorting we did with a 100 ohm resistor. We can see here that the damping is happening in the plotting part, and here we are going to see the signal decay. Then we are going to put it in a logarithm plot just to see if the decay is really exponential. And how we see that? If it is exponential, it should be a BV formula, and we should observe a line in a logarithm plot. And we are going to see the on and off resonance also. So here we go. We see here the off resonance signal mode, and here we see the on resonance signal. So in the on resonance signal, we don't see the oscillatory motion. In the off resonance signal, we see the oscillatory and the decay. So if we put here in the logarithm scale, we see that it is a line. So this envelope here is an exponential, okay? So next experiment will be the relaxometry emulation for different decays. We already proved that we can do the exponential decay, but we didn't prove that we can change the relaxation time. And this is important for relaxometry because we can say that if we change the sample or the conditions that the sample is, such as if it is solid or liquid, we can change the relaxation decay time. And for this, we can use, for example, another resistor. There, we were using a 100 ohm resistor. Now I put 200 ohm resistors in parallel, so we have 50 ohm resistor. So now the break should be much stronger. Let's see this in practice. Let's change the camera here, and let's change for the Excel plot. I'm going to change here the 100 ohm resistor for the 50 ohm resistor, putting it here. Here we have it. Let me now click in fixed value resistor, and let's see oscillating. See, the start is equal because the pulse will be always the same, but it is already showing that it is decaying much faster. So the break is stronger, so we have a different decay time, a different relaxation time. And we are going to see here in the logarithm path plot that it is also a BV break, so it will be a line also. Showing that this envelope is an exponential envelope. So let's wait it. Here we have a line. It has a different slope, showing us that it has a different decay time. To make it clear that it is different decay time and we can plot different decay time, let's short the coil now. And now we have the minimum resistance of this coil, so the maximum break available. So let's put it to calculate again. And here we go. You can see that the decay is much faster, so the relaxation time is very small. And we can also see that the envelope is an exponential. This is easy to see now. It wasn't easy to see in the graded value of the resistance, but now it's easy to see as we diminish the resistance a lot. Now it's only the resistance of the coil, which is close to 100 ohms. So this is somewhat important to show the students and what is the difference and what is the meaning of the relaxation time. and what happens when you change the relaxation time. So here we have these three plots, all exponential decays with different relaxation times. Just to show the exponential, let's put it out of the logarithm value. So here we go. Another interesting experiment we can show with our analog. So now that we show that we can emulate exponential decays with different decay times, with different relaxation times, it's time to show that we can emulate different types of decays, such as the multi-exponential decays and a Gaussian decay. Well, multi-exponential decays appears in NMR signals, for example, when we have confined sample in pores of different size. And Gaussian decays appears in solids with high abundance of nuclei of hydrogen, for example. So these two decay types are present in the NMR experiments and can be emulated in our analog. So how do we do this? So for this, we're going to use the potentiometer attached to the servo. This way we can change the break with time, and therefore changing the break, we can change the curve, we can change the shape of the curve. So here we have our two wires that come from the potentiometer, and we have to put it in the damping coil here. Let's put it right here. And we have a battery here that will change, that will turn the servo. Why we have an external battery? Because if we use the computer, then we're going to have some noise, and so it's important to have an external battery. And now we can go to our program. So here in the program, you need to select the type of the curve you want to choose. So first I'm going to do the stretch exponential, and I choose the speed of the servo. 0 is the fastest speed, and then you can go to any type of speed you want. 4 is a good speed for a slow speed. Now you send the parameters, and you click stretch/Gaussian. Because we select 1, it will do the stretch exponential. Try to hear the servo motor ticking. You see, at first it looks like an exponential, but now it's going flat. This is because it's a multi-exponential decay that can be modeled by a stretch exponential. Let's wait until the end and see the graph here. So here we can see the stretch exponential decay like. It's not in the log mode, but if we put in the log, we can see that it is not anymore a line, it is more like a curve. In the end, it turns like a line because the servo is starting to change very little. And now we can do the Gaussian decay. Just put 0 here. I'm going to put it to spin very fast, so 0 here also. I will send the parameters and put stretch/Gaussian again. It will do the Gaussian now because I sent 0. Let's see. Now you can see it decaying very fast, and now it will start to slowly stop decreasing. And this looks like already a Gaussian envelope. And we're going to see here a Gaussian-like curve also. Remembering now that I'm not in the logarithm anymore, but it's just to see the stretch exponential like and the Gaussian. So it's easier to see when you don't have the oscillation. You only have the amplitude, the on resonance detection signal mode. So let's see. Here we have our Gaussian decay. It's very neat, beautifully explained, but this is not the only thing we can do. Well, the last experiment I'm going to show you using the NMR analog is the T2-T2 2D correlation map. I won't be able to show you the experiment because it takes a lot of time, usually more than 4 hours. But you don't have to worry about it because you have just to press a button and go away, it does all automatically. So let's talk a little bit about 2D correlation map and how we emulate this using NMR analog. So basically, you're going to use a pulse sequence to modulate the amplitude by a certain type of decay. And then you're going to alter this this evolution time and see what happens after this using another decay. So we're going to have two decay types. In the first one, we'll be modulating the amplitude that will appear in the second decay. To emulate this process here, we use a relay that is shorted at first and then it lets open. So when the relay is shorted, we're going to have the damping coil with a 10 ohm resistor only. But then when the relay stops to be shorted, we are going to have a 110 ohm resistor. And this time we change. This time it stays on. This blue part here, we don't see in nuclear magnetic resonance experience because it's the amplitude modulation we do using a pulse sequence. We only see the second part, which is the decay that had the amplitude modulated by the first mixing part. So here we can see the amplitude was modulated by the first decay, which was the 10 ohm resistor, and then it was modulated by the 110 ohm resistor decay. And what we can see doing an inverse Laplace transform is that we observe the two decays. The first decay appears right here, and the second decay appears right here. So as we were using two resistors, two fixed value resistors, we saw the decays were exponential. So we only have one decay time at each, and so we have a circle here with a decay time of each part of the experiment. The first that modulated the amplitude of the second that is shown here. So we can change the evolution for a potentiometer, and now we can use exponential decay at first to modulate the amplitude, the same as before, but now we can do, for example, an evolution at the second part that is not exponential decay. For example, this we use the stretched exponential decay like using the potentiometer. And now you can see that the 2D correlation map changes. So you can emulate this experiment using the analog. Very interesting, right? So these are the experiments we can do using our mechanical analog. Of course, you can teach a lot of other things like the circuit gain and also about the construction of an NMR's digitalization circuit using this. There are a lot of stuff to be done, and it's very simple to do. So it's a good way of teaching NMR basics principle, and it's very didactic, and it's a good tool for classroom. Thank you.